Hi, this is Tim Malloy with the far overdue video 3-2 Biot-Savart Law. This is uh, this is number 4. So here we go. Consider the following figure. I will describe it in a moment. I'll just let the problem do it. A conducting loop in the shape of a square of edge length L equals 0.42 meters carries a current current I equals 10.4 amps, as in the figure above. Calculate the magnitude and direction of the magnetic field and the center. So each one of these sides, each one of these sides is at 0.42 meters, and they all carry this current, which we know travels counterclockwise, right? No, sorry, regular clockwise, based on the given direction here. Okay, and so they ask for magnitude and direction, and real quick, we could use the right-hand curl rule for direction, and we know on the outside, or I chose this top piece, by the way. But it applies for any piece you choose. So on the top, our magnetic field will travel out of the page, and on the inside of at any of these points, any of the parts of the loop, the field will travel into the page. So that's pretty basic stuff. You should know that by now. And this problem is about the Biot-Savart law. So let's start there, because it looks like we know that we can use the Biot-Savart law with wires, and the square looks to be made up of 4 of them. So here's our Biot-Savart law. So dB equals mu naught times current. Okay, I guess I should say everything in terms of what it is, not just the symbols. So d magnetic field equals mu naught times current over 4 pi times the r distance times dl cross radial direction over over distance. I guess changing distance. So, anyways, this is our magnetic field in free space equation. This is our this is just the kind of that X factor from the Biot-Savart law that makes the Biot-Savart law what the Biot-Savart law is. That made sense. Okay, and then simplified it a little bit, just moved ours to one side. And then just to explain the Biot-Savart law, because yeah, I can write it all out like this, but it's not going to mean anything to us if we don't know what it represents, because if we don't know what it represents, we won't be able to use it correctly. So again, this part was just a standard magnetic field equation that we discovered in one of our labs. So then notice as we choose points on this wire that the magnetic field will not always be acting perpendicular, right? So this vector r tells us just how perpendicular, this cross product just tells us just how perpendicular this magnetic field is from our point to our chosen object, in this case a wire. And then this, again, this r is the distance, by the way. And this dl, tells us that we're choosing an infinitesimally small piece of wire to look at, and it also tells us the current direction. And, in this case, we're going with the current. Okay, I hope that made sense. And then this is just a simplification of that cross product, by the way. So now if I expand this a little bit, and I actually, this is practically identical, oops, sorry, too far. Practically identical to what I did here. I just added this a. So the sine of theta equals a over r, and then r equals a cosecant of theta. So that's cool. We're going to be able to plug something in for the r down here. Because, mu naught current, 4 pi, we know all of that, but that, sorry, let me circle this. These parts we still gotta put into regular people terms. And then, so that's our R, perfect. Now I want to get our L, which I guess I didn't label in here, but yeah, the L is length of this whole wire. So our tangent of theta equals this opposite over adjacent. And it's negative because the idea is that we're reading from the left of A to A, because it's like a triangle. I think we kind of did this in math class. It's like a triangle, right? So, oh my God. Okay, let me straighten it. Perfect. Okay, because it's like a decreasing triangle, decreasing, decreasing, negative for that. And I'm sure eventually it will be positive because it will grow, and that angle will grow. Does that make sense? I think it does. I hope so. Or at least the idea that, we the angle decreases as we, I guess it increases. Okay, well the DL, the length decreases as we go on, and then increases. Anyways, negative against string left a, and then we set it equal to L, and then since in the equation we use DL, we derive both sides. I think that makes sense. And then we get DL equals A, which is again perpendicular distance. I think I mentioned that A cosecant of theta d theta. We have that sine theta from when we simplified the cross product. Here's what we plug in for DL, I think, yes, DL. And here's what we plug in for R. And then we simplify, and then we get this. Notice how we have that d theta and that, I'm going to just write this out. We have that d theta and we have the dB, so I think we're going to want to integrate. So we'll come back to this in a second. Oh, look, I'm blue now. Okay. So we did integrate, and that is all nice, but now what should we use for our bounds? So on one end, we're going to use the angle at the, I guess in this case, leftmost point. Oh, this is a little incorrect. Let me erase that. Oh, sorry. That's just some leftover work I had before I corrected some of it. Anyways, this theta 1 is our leftmost angle. Theta 2 is our rightmost. A simple integral there. And now, okay, this is all nice and all, and we can actually work with all this because we have A. We have A. It'll be our perpendicular distance. We can find that, which I do below here, because we know that half of L is 0.21, and then if it's a square, it'll be that will be 0.21, and then this will also be 0.21 because it's half of the side length. And then the point P is just what we're finding. So our angle, this is a 45, 45, 90 triangle, very familiar. Angle here is 45. And then what we actually want to do at this point is it's not this interior angle. Sorry, it is not the interior angle, but it is the exterior one. Yeah, okay, perfect. Okay, so theta 1 equals 45 degrees, theta 2 equals, not theta 2, don't know why I wrote that, but 135 degrees. Plug those in right here, simplify those right here, simplify even further for this. So yay, we have our general formula for, what would I call this? Magnetic field of a wire at a point. Magnetic field due to a wire at a point. That makes sense, okay. So back to the equation, or not the equation, the question. We got this square. So maybe if we find the magnetic field for one of these, we can multiply by 4 and be okay because none of the currents or magnetic fields are opposing each other, are all traveling into the page. That makes sense. Okay, where I lost myself. Okay. So 4 wires acting at one point in the same direction. So I just took what we have above here, plugged in my known values, multiplied by 4, and I explained how we got everything that's our current that was given, mu naught, whatever. That's root 2 from all the garbage we did with the theta angle. Constant, perpendicular distance, perfect, 28 micro Tesla. Okay, wonderful. So that's part A all done. Now on to part B. If this conductor is reshaped to form a circular loop and carries the same current, what is the value of the mag field at the center? So, much like a problem from before, but we have a circle now. So let's go. So this is just starting again. It's like Biot-Savart Law. It's like I integrated this part. That's what I did to get here. So I'm just going back to that original law, and now I'm playing with it in a different way. So since you understand that here I'll just do a little drawing again. That the magnetic field will not always be perpendicular to the line, to the wire. When we use a wire, it will always be perpendicular to the circular wire because it's a circle. It always forms a 90-degree angle like so. Okay, so we can plug 90 in for sine of theta, that's 1. So now we're just left with the integral of ds, or it's, you call it ds, but I like dl just because, we use L for length. Maybe there's another reason why you use ds, but anyways, I think for me it's easiest to just use dl. So we integrate that for L, and then 2 radians you do length equals r times theta. I like to use radians more, but anyways, we just do that really easy. Plug her in there, cancel that out. Now, okay, that's fine. We have this, this. For theta, we're going to use 2 pi because that's what they ask us. That is what they ask, because we're using radians, and we're doing the whole circle. Okay. Now, what about this r value? Because yeah, we have a new circle, but they're using the same length as all of that square material in a new circle. A little weird. Okay, so we do know circumference is just all that length of the squares, the length of the sides of the squares. Okay, then we set that equal to circumference, and then we solve for r. Perfect. And now we have everything we can plug in. Constant, current, 2 pi, 4 pi, constant, right? No, yes, kind of. Anyways, and then 0.84 meters over pi, and we get 24.4 microtesla. And it also does ask where does the magnetic field point, and it's the same idea as before, where this part is inwards, this part is outwards, so we're going to use outwards. Okay, again, 28 microtesla, all good. Into the page, 24.4 microtesla, into the page, wonderful. So here are my takeaways. Driving the equation from scratch really stinks. I do understand most of the process, but even while I was doing this video, I was understanding things and kind of viewing things in a new light. It's a whole lot different when you have to explain something rather than just something being explained to you and you just nod your head and say okay. And then part B wasn't too bad. The circle stuff was really easy because you don't have to worry about the angle because the angle is always the same. Okay, that should be it for the video. Thank you for watching.